An important distinction to make when you are discussing probability is to understand the difference between independent and dependent events. When something is independent, it means that the outcome of the first event does not affect the probability of the second event. They are completely unaffected by one another. Whenever you do have dependent events, however, then what we see is whatever happens on the first in the first event or the first draw or the first coin flip, if you will, that could very well impact your probability of your next event. So ask yourself the question, for example, if I were to flip a coin 10 times in a row to see whether or not I get a heads or a tails, would that be an example of independent or dependent? And you're right, that would be a series of independent events. The result of the coin flip on the first flip has no bearing on what happens on the second flip. What about if you're drawing cards from a deck, or let's say you're drawing two cards from a deck? If you draw the first card and then you place it back into the deck, then your next card, we would see that these are both independent events. The first draw doesn't affect the other. However, if you draw the first card and you hold on to it before drawing the second card, now you've affected the probability of your second draw. So let's talk about these cases. So first off, let's try this first problem here where we're drawing two cards from the deck. What is the probability that both of the cards you draw are face cards? So let's talk about what happens without replacement first. Without replacement, meaning we don't put the card back, we draw one card, we keep it in our hand, and then we draw the next card. So what is the probability that you'll draw a face card just by itself? That would be 12 out of 52 because there are 12 face cards. Now, what is the probability that you draw a face card on your next card? Because now there is one less card to draw from, there would be 51 in the denominator and 11 in the numerator. Again, that assumes that you drew a face card on that first draw. So something like this here, we can just quickly simplify and you should get 11 over 221 once you've simplified this all. So that's the probability without replacement. What about the probability with replacement? So with replacement, meaning you draw a card, and after you draw that card, you place it back. So this time, the probability is still 12 out of 52 for that first card, but now that you've placed a card back, you're kind of starting from scratch again. What is the probability that you then get a face card on your next one? That's also going to be 12 out of 52. And this is just equivalent to 3 out of 13, all of this squared. So you should then get 9 out of 169. Okay, that's the probability of without replacement. Let's try another problem. Let's switch to blue. So let's say you have a situation where you have a sales representative and they make a sale on 1/3 of all calls. So this is kind of similar to like an athlete, for example, a baseball player batting with a batting average, or a basketball player's field goal percentage, or a quarterback's you know completion percentage, or something like that. So on average, we'd say that this sales rep makes a sale on 1/3 of all calls. If the representative contacts 5 potential clients, in other words, they make 5 phone calls, what is the probability that this sales rep makes a sale on all 5? Well, let's think about this. First, ask yourself, is this independent or dependent? And you're right, this is independent. Let's kind of ignore the psychological effect of maybe not making a sale and how that might affect you on the next one, but let's just treat each situation on its own, in which case the probability that they make a sale in the first phone call is 1/3. What about the next phone call? What is their probability that they'll make a sale? It's still 1/3, right? That's going to be the sales probability for each call. And this is going to just keep on going for the third call, the fourth call, and the fifth call. This is going to come out to 1/3 to the fifth power, which simplifies out nicely to 1 over 243. Okay. Now let's try an example where that sales rep makes a sale on at least one sale. Well, so what's the probability that they'll make at least one sale? And one way that you could do this is you could say, all right, what's the probability that they'll make one sale or two sales? Remember that word at least creates a couple of different or situations, or 3 or 4 or 5. And this is a lot of adding. I don't really want to deal with this. We could leverage the idea of a complement here, because we could say, hey, maybe it might just be easier to find the probability that this sales rep will make 0 sales. And just subtract that from 1. In other words, subtract that from 100%. That's the complement there. So what is the probability that this person doesn't make any sales? That means on the first phone call, their probability of not making a sale is 2/3. And then on the second phone call, their probability of not making a sale is again 2/3. And just like the previous problem, we're going to keep on repeating this. So this is the same as 2/3 to the 5th power. And so what does this come out to? This would be 243, if I just want to clean this up, minus 32 over 243. And our answer would be 211 over 243. Okay? All right, so we can just summarize this. Probability of at least one sale is equal to 1 minus the probability of no sales. All right, let's try another problem now. So let's go ahead and let's talk about the shipment of light bulbs here. So this is kind of similar to the problem that we did in the previous lesson with the professor choosing 10 problems for the test out of the 20 that are available. But I just do this just to kind of highlight the idea of independent versus dependent. So first off, make sure we understand the problem. There's a shipment of 30 light bulbs, and 5 of them are defective. We don't know which ones. A consumer buys 4 bulbs. Let's find the probability that all 4 bulbs that this consumer bought were good, that they were non-defective, okay? Now, ask yourself here, is this an independent or dependent situation? Well, this would be dependent here. This is going to be a dependent situation because these bulbs are not replaced. It's not like a consumer is choosing a bulb, checking to see if it works, and then placing it back. They're just going to be taking 4 bulbs. So what is the probability that all 4 are good? So let's think about this. First off, what are the number of ways that you can choose 4 bulbs from the 30 that are available to you? That would be 30 choose 4. Okay, so these are 4 chosen from the 30 total. Okay, now let's think about quote unquote the success events or the successful events. If we choose 4, we want to make sure that all 4 are good. So we're choosing 4 good bulbs from how many are good to begin with? 25 good bulbs that are available. This is 4 chosen from the 25 quote unquote good bulbs, right? I don't mean like morally good, I mean like they work, right? So this would be our probability here. If we simplify this, this comes out to 25, 30 over 54, 81. There's our probability there, okay? Now let's try to find a probability that exactly 2 are defective. So what's another way of stating this? It means that 2 are good and 2 are defective. So let's find that probability. Well, what is the probability that 2 are good? Well, this time we're choosing 2 from the 25 that are good. Probability that 2 are defective, that means from the 5 that are bad or defective, we're choosing 2 from those. And again, we've got 30 that we're choosing from a total. So this is going to come out to 200 over 1827 as our final answer. Okay. And I'm going to let you try part C on your own, and you can check my solutions. But again, think about that word at most, and what might be a more efficient way of going about doing this, right? Hint, you might want to think about the 1 minus the probability that all 4 are good and 0 are bad. Okay, so go ahead and try part C and D, and you can go ahead and check my solutions with what I have in Google Classroom. The final thing I do want to discuss with you all is the idea of binomial probability. Now, this happens in unique cases when, first off, we have n number of independent trials. So when we're dealing with independent probability or independent events, and n independent trials, and the idea is that each trial has just 2 possible outcomes, either success or failure, or something like heads or tails, right? The idea of the probability just really being binomial, right? Then we can use what's called binomial probability. And if you look at it here, it's really just an offset of the binomial theorem. Well, just to break a couple things down, the probability of R success in n number of trials, we would say n choose R, where again, n is the number of trials And R is the number of successful events. And we'll break this down again. P would be the probability of success, and then Q is the probability of failure. Such a depressing word, failure, but just basically the opposite of success, I guess. All right. Now, instead of me giving you separate problems, I want you to actually go back through your notes and see, was there a problem here that we actually could have applied binomial probability for? And the answer is yes. Let's go back to this sales representative, right? And ask ourselves, how could we have used binomial probability in this problem? Well, in this particular case, if I wanted to find the probability that this sales rep made a sales for all 5, well, what is our N? Well, there's 5 phone calls being made. And if that sales rep is getting a sale on every single one, how many successful events, quote unquote, are we looking for here? This would be 5 sales. Well, P here, again, the probability of success is 1/3, whereas Q was 2/3. So how could I use binomial probability here? I would say my N choose R would be 5 choose 5, which is just 1, times P to the R power times Q to the N minus R power. In other words, this would be 1/3 to the 5th power, and Q was 2/3. What's 5 minus 5 there? We would say to the 0 power. And again, what do we see all of this is? This is equal to 1. This also is equal to 1. And what I have left over is exactly what we ended up doing in this previous problem. It was just all of this here. So it's just another approach that we could have taken here, but I just wanted to do it to illustrate how we might use binomial probability.